of the ROSIN FTP, which was funded by the ROSIN initiative. The software, I will get into a little bit more detail on it, but the overall idea was to try to map the robotics components or the robotic world with the automation world. But before we get into a little bit more detail, I just want to some of our participation of INESC TEC in research projects. Throughout the years, as I mentioned, we have worked in collaboration with the automotive sector mostly, and also recently with the aerospace sector to develop automation and robotic systems, specifically mobile manipulators to perform either manufacturing operations or intralogistics tasks within European manufacturers of these industrial sectors. And we also have put a little bit of an effort in the last few years into human-robot collaboration, and here in the videos that is hopefully being showcased in the presentation, you can see two examples of this. On the top, we can see the Scalable project, where we developed flexible automation and robotic solutions for the automotive sector, in concrete Peugeot, Citroën, and a company here in Portugal, Simoldes. And here in the bottom left part, we have a project which we developed for Renault in France. So it was basically a mobile manipulator to provide these assistive tasks to operators within the insides of a vehicle. All of these videos and all of these projects that I presented here have the same feature of actually featuring our ROS-CODESYS bridge, either for establishing communication between the ROS ecosystem and some kind of hardware which only spoke automation languages, or to even integrate the robots with the automation production line. And I will get to particular details in a little bit. So going into a little bit more of the background for this development of the ROS-CODESYS bridge. So the challenge that we face as a ROS developer was the fact that we found out that many times it was time-consuming for us to develop or integrate industrial communication protocols within ROS. Sure enough, there is already some effort and some very valuable tools within even the ROS Industrial Consortium ecosystem to provide communications with field buses and automation protocols, but we believe that there could be a more systematic way and a more efficient way to perform this kind of connectivity. And thus the ROS-CODESYS bridge started initially as a master thesis project, but then it evolved to being this funded ROSIN initiative. And the solution here revolves around a shared memory interface that enables the communication between ROS and between CODESYS, which is a soft PLC application that can then be used kind of like a relay or a middleware between the robotic world and the automation world. So in other words, CODESYS could be responsible for communicating in field buses, so EtherCAT, CAN-open, Modbus, and so on, but also implementing connectivity and interoperability with higher level manufacturing systems, such as the features provided by, for example, OPC UA. And all of these types of communications were communications that we explored throughout the project. Going into a little detail on the architecture of the tool. So we advised this solution to be running within an embedded device, and specifically we target this BeagleBone Black embedded system, which is a very similar structure as a Raspberry Pi, but has the feature or the added feature to have a real-time capabilities, because it has a dedicated real-time processor. So it's very suitable for us to have this kind of system and using these real-time capabilities to communicate with the industrial equipment. And by having within this very same embedded device an installation of ROS and also a runtime installation of CODESYS, so in other words, a soft PLC running within this embedded system, we can establish inter-process communication, shared memory communication, if you will, between the ROS ecosystem and the CODESYS ecosystem. And since we all should know that ROS is a distributed system, this ROS installation can communicate externally to the robot computer, for example, which could be a dedicated x86 architecture CPU that can run the general infrastructure of code. For the communication, as I mentioned before, we are relying on this shared memory interface. The way that we structured this was to, why we chosen to have this path is to keep the latency of communication as low as possible, but at the same time, we have a structure or a set of methodologies to enforce the reliability of data. So we have these semaphore structures, basically certifying that the access to this shared memory data space can only be accessed by a dedicated component, either the ROS node or the CODESYS application at any given time. And then on the ROS world, the communication through other nodes in the system can be established by simple ROS topics. And on the CODESYS side, this communication with industrial equipment can also be instantiated through industrial protocols, so field buses in other words. The first challenge that we faced, and perhaps one of the major ones, was to map the ROS messages into data structures which could be intelligible from the PLC domain. In other words, what we had to do is to map the ROS primitive type, so the Boolean structure, the integers and the strings and the floats and so on, into types of messages first that were converted to C++, and this was easy enough to do, but then map the C++ structure to IEC 61131-3 compliant data. So as probably some of you are aware, this is the type of, or the norm that defines most of the PLC programming infrastructure, and the challenge was to provide this translation between both ways of synthesizing information. Currently, we have full support for most of the implementations. Even the ones which are listed here as work in progress or partial supports, at the moment, we do have already strategies for implementing them. We cannot enforce them or certify them between codes to be able to be used into industrial applications, because we think there should be a little bit more development and a little bit more experimentation on that side. But nevertheless, we have application examples where in our projects we are using this type of communications. And here the most challenging things was to map the time parameters and also some conversions with ROS implementations of arrays without a dedicated fixed length, which is not possible in IEC, in the IEC norm. But yeah, we have methodologies for already establishing this kind of communications nevertheless, although not fully 100% industrial proof at the moment. The ROS implementation. So I have here a little bit of code symbolizing the class structure of this Robin application. I will not waste too much time on this because I think the next slide is a little bit more valid for the usability point of view. But I just wanted to highlight that the communication between systems in ROS or applications in ROS with this infrastructure, this Robin infrastructure, our software, can be done using a topic-based implementation. So we rely on the publisher-subscribe methodology of ROS to have a dedicated node of the system collecting subscriptions from topics which have been listed as topics of information that should be forwarded to the PLC, and provided the same methodology on the other way around. So having this node output information to topics that then can be consulted by the ROS ecosystem. And this is the way that the shared memory synchronization methodology works periodically to accomplish this bidirectional communication. From the point of view of the developer, what the developer needs to do is just to create a very simple application. This is the totality of it, where we basically describe what is the topic that we want to write to the shared memory location, and what is the topic, in this instance, for example, that we want to read, and then it's just a matter of invoking this class, this ROBIN class, and invoking this read or publication methodology. It's very, very easy to create this ROBIN middleware node to provide this communication. On the PLC side, we tried also to simplify a little bit the developments, and this is a picture of the structure of a CODESYS environment. The main thing that we had to do in the PLC world is to import a project which we have generated, which already has mapping for most of the common type, or all, to say it better, all common types of ROS standard messages and sensor messages. So all of the messages from ROS which are default. And basically in the program, the interface for configuration can be done via a single program, a very simple structured text program, where we have using 2 or 3 commands, 2 or 3 instructions, just basically doing the same analogous thing that we did on the ROS ecosystem. So configuring which were the topics or the names of the shared memory that is mapped to read and to write, and this should be, of course, mapped according to what was defined on the ROS world. More than that, we simplified things even further in the last few weeks and months of the project, in the sense that we allow and we have developed this automatic code generation, in the sense that if we have a PLC software project in CODESYS already using a set of defined variables, we can invoke, and this is what this video is showing, we can invoke the automated capabilities of the ROBIN software to basically generate in an automatic fashion the code that is then imported or exported, to say it better, automatically to the BeagleBone Black via an SSH communication. So in other words, a developer needs only to worry about the configuration of the variables that he or she wants to import or export from the CODESYS side, generate the automatic code behavior, and everything is translated to the ROS ecosystem. So on the ROS side, developer needs only to publish or subscribe to the topics that were managed. So I think this is a very straightforward way of addressing the issue and addressing the problem. Finally, here on this slide, I have a video showcasing an example of application of this software in one of our projects, and specifically this one, the Scalable 4.0 European project, which finished a few weeks ago. In this specific demonstration that was recorded in the factory with the actual Scalable 4.0 robot, also a few months ago, we are using the ROS-CODESYS bridge for 2 dedicated or 2 separate communication interfaces. The first one that I want to highlight is pictured here, represented here on the left side of the image, and is related with the communication between the ROS ecosystem and the conveyor PLC. So this is basically in the factory, we have this dedicated multi-product assembly line where we have these sensors, which was pictured a few seconds ago in the video, which are basically laser sensors that detect the positioning of the objects to be picked and inform the robot through this ROS-CODESYS software implementation that there is in fact a given type of part at this position. And the way that we do this is to enable a communication between the BeagleBone Black, running also the ROS node, which was generated automatically from our CODESYS project, and then having this CODESYS project communicate via Modbus with the conveyor PLC, which then of course has its own project that is reading the sensors and also actuating on the controller for the motor that movements the conveyor belt. The other application example that we are also running on this very same demonstration is all connected to the robot hardware, and specifically the manipulation controller. So in this instance, we are not using any interface for communicating with the controller using its ROS library, or well, relying on any kind of direct software communication or interoperability mean. What we are doing, in fact, is establishing direct communication with the robot controller through Modbus as well, to retrieve not only its position, its Cartesian position, but also to issue commands for the robots to move around. So in this instance, for example, the location of the objects is computed by the vision system in real time. And what we are doing is using this information that is computed to then inform the controller what is the final position of the object that should be picked. And we are, of course, in this situation also relying on the ROS-CODESYS environment to do this as well. Finally, to conclude my last slide, just some notes on conclusion. Two things that I want to highlight here. First is that this software has been released as an open source contribution, and it is accessible through this URL. So it's in GitHub within the Scalable 4.0 organization, and the domain name or the project name is Robin. So it's very easy to access, and it's of course an open license. So it's Apache 2.0 software, so it's open source and open license, and you are free, of course, to use in your projects. One thing that we also are doing is to have the software running within the CI infrastructure. So we are periodically checking, trying to release new versions and checking its quality and the coverage of the tests that we have. Right now, we are not at a very high mark, but we plan to improve this in the future. And also in our roadmap is the release of this software infrastructure to as an official ROS package. And in parallel to that, also work on the conversion of this infrastructure to ROS-2. So the new version of ROS that is well, already available. Second thing, just to finalize, is that all of this that I explained to you today with a very high level overview, due to, of course, the time restrictions and well, the level of detail that one can go into this kind of presentations. But nevertheless, there is this paper that we published. It was published a few months ago, I think in June, if I'm not mistaken, which basically explains all of our methodology, all that is behind the software that we developed, and also some concepts that I was not capable of bringing to this presentation, but I would advise anyone interested in getting to know more details to check out this publication, and also have here the URL for it. And I think this concludes my presentation, and of course I will be more than welcome to answer any questions that might have been. Thank you.
Thanks, Rafael.